So, greetings, once again we meet to continue our discussion on the interaction of electromagnetic radiation with matter. In the previous classes we have seen how the electromagnetic radiation behaves when it interacts with a matter, interacts with the matter. So, we have seen reflection, refraction, diffraction and other phenomenon, and then I have also discussed about the slits, monochromator slits, because whenever we want a particular radiation corresponding to a specific wavelength, we need to choose from the given bundle of electromagnetic radiation from different frequencies what we want to choose. So, that is how that is the job of monochromator slits, and this figure I had shown you in the last presentation. What it means is basically, so normally what we have is a source of electromagnetic radiation and then I have a lens or something. So, if the radiation is coming, this is a concave mirror which will give you all the radiation in the parallel form. Okay. So, here lens or a prism or something like that will give you different wavelengths. Suppose you put a prism, so all you need is a slit, and this slit is nothing but a mechanical plate with a small hole in that, and this slit can be moved. So, if it moves here, the radiation will come from here, but if the slit moves up, the radiation will be coming through this. So, depending upon the movement of the slit, we will be getting different wavelengths, and when we get different wavelengths, if you plot the energy of the electromagnetic radiation wavelength, this is lambda. So, the peak what you will get is something like this. This is the wavelength what you want to use, desired wavelength. But you will also get what is some unwanted but nearby radiations. So, this will be lambda 0, this will be lambda 1, this will be lambda 2. So, the slit will give you a mixture of lambda 0 plus lambda 1 plus lambda 2. So, lambda, therefore, the wavelength what you get would be lambda 0 plus or minus delta lambda. So, delta lambda means lambda 1 may be on the right side, that is higher wavelength, and lambda 2 may be on the left side, that is lower wavelengths. So, this is what I was trying to show you in my last slide. So, in this figure what I have is I have shown the same thing as lambda 1, lambda 2 and lambda 3, and you will always end up with a bundle of wavelengths which is having maximum peak is what you desire, let us say 430, but then you have to add delta lambda to that. So, delta lambda may be 5. So, you will always end up with 425, 430 and 435. So, plus or minus 5 nanometers in depending upon the lenses or the slit. So, the requirement of a particular wavelength is always a function of the slit diameter. So, design of the slit is always very important in all spectrophotometers as well as all other spectroscopic techniques also. So, this is what I was trying to tell you. Our next point of discussion would be the photoelectric effect. This is again part of our continuing discussion regarding the interaction of electromagnetic radiation with matter. Now, when we say, assume that in the just like in the previous slide, we have got lambda 2 is the wavelength what I got, and this lambda 2 wavelength, if it is made to interact with a particular metal, or a photocathode. What is a photocathode? A cathode is coated with alkali metals. So, electrons of varying kinetic energies are emitted from its surface and fly over to the anode, because electrons are attracted to the anode. So, as long as the voltage V is supplied between the anode and cathode is positive, it produces a current. So, if I make the take a monochromatic light, however pure it may be. Okay. So, if I make it fall on a metal plate, when the metal electromagnetic radiation falls on the metal plate, the electrons are ejected. Where the ejected electrons will go? They will go to the cathode. So, if I put a cathode in front, I have a material here, radiation is coming and falling here, and it will eject electrons. Electrons will be attracted to the cathode, and to the I will also need an anode. So, if I maintain a positive difference between the potential between anode and cathode, electrons are always going towards the cathode, and then a small amount of current will be generated. This is the effect of electromagnetic radiation falling on the falling on a material that is interacting with a metal whose work function is low, which allows electrons to be released from the metal, that is alkali metal, and a current is produced. So, if I want to know what is the quality of the electromagnetic radiation, I must let it fall on a photocathode and measure the current. So, the measurement of current gives me a tool to assess the electromagnetic radiation. So, when the voltage across the phototube is adjusted such that the anode is negative, photoelectrons are repelled by the anode. You see, electrons carry negative charge, anode is also having negative charge. So, they get repelled and photocurrent decreases. So, if the potential difference between anode and cathode, if it is increasing, if it is high, the current will be more. So, it is measured as a function of the applied voltage at which the photoelectric current reaches 0, multiplied by the electronic charge, that is coulombs. So, that gives the kinetic energy of the most energetic electrons in joules. It is a very simple process. All you got to do is measure the current and multiply it by 1.60 into 10 raised to minus 19, that will give you joules. So, when maximum kinetic energy for various coatings are plotted as a function of the radiation frequency, we get a straight line, and the slope is Planck's constant, that is 6.6254 into 10 raised to minus 34 joules per second, with an intercept W, and this W is known as work function. So, this work function is the characteristic of every alkali metal or every metal for that matter. So, until the work function is reached, the electrons will not be ejected from the cathode. So, the plot what we have been talking is given by the equation Kem is equal to h mu by minus W, where W is the work function. mu is the frequency, h is Planck's constant, Ke is kinetic energy of the metal. We can also write it as E is equal to Ke into m plus w, or in several ways which I have already shown here. That is also equal to hc by lambda. What is h? H is Planck's constant, c is velocity of light, and lambda is the wavelength. So, the work function W, as I was telling you, is characteristic of the surface material, and the work function represents the minimum energy of the binding the electron to the metal atom. If you provide excess energy, the electron will be going out, it will be flying away, and from the when it is released from the metal, it will fly towards the cathode, and during that process the current will be generated. Therefore, it can be concluded that no electron can be ejected until the sum of the work function is realized, and that can be quantified as kinetic energy of the metal, K dot E m. Therefore, the energy is not uniformly distributed over the beam front, but it is concentrated in packets or bundles. So, this is a thumping confirmation of quantum mechanical theory. What it says? The energy difference between the two levels is always a constant and it is not continuous. That means, if I keep on supplying the energy continuously, you will not see any electric current, but the moment it reaches a particular value and exceeds, you will start seeing the current. So, this work function is a very important concept of the electromagnetic radiation. So, the equation permits the calculation of the energy of the electromagnetic radiation of known frequency or wavelength or vice versa, either way. So, this is the important thing. Now, I want to demonstrate to you how we can calculate the energy of a radiation. Now, in the example in front of you, I have this 5.5 angstroms X-ray photon. So, I want to know what is the energy of this wavelength that is coming out whenever I have taken electrons and bombarded it on a metal and X-ray is generated. The X-ray generated is having a wavelength of 5.5 angstrom units. What is its energy? So, the solution is very simple. We use the equation E is equal to h mu, that is equal to hc by lambda, and what I have here is all I got to do is substitute the values of h, that is 6.63 into 10 raised to minus 4 joules second, multiplied by speed of light hc, c is 3.00 into 10 raised to 8 meters per second, and then I have to divide it by the wavelength, that is 5.5 angstroms. Normally we convert it into meters. So, I multiply it by 10 raised to minus 10 meters per second. 1 angstrom is 10 raised to minus 10 meters per second, and if I put these values, what I get is 2.26 into 10 raised to 3 electron volts, that is the unit. Therefore, given any wavelength, I can calculate the energy of the electron, energy of the electromagnetic radiation. Vice versa, if I know the energy of the radiation, I can always calculate what is the wavelength of the electromagnetic radiation. Take a look at the next example. So, next example is again, it is a wavelength I am giving, that is 430 nanometer. I am calling, instead of calling electromagnetic radiation, I am calling it as a photon. So, calculate the energy of the 430 nanometer photon of visible radiation. This falls in the visible range. So, how do? I just have to repeat what I have done in the last example. So, write E is equal to hc by lambda, h is 6.63 into 10 raised to minus 34 multiplied by 3 into 10 raised to 8. divided by the wavelength, that is 430 nanometer, that is provided to you, and then that is multiplied by 10 raised to minus 9, that is meters per nanometers. So, if you solve it, you will end up with 4.6255 and into 10 raised to minus 19, that is the energy of the radiation, that is usually expressed in kilojoules, and if I do that, I will end up with 278.4551 kilojoules per mole. This is a very simple this thing, and basically what we have been discussing is the part of blackbody radiation. Now, what is this blackbody radiation? If you take any black material, metal for example, you keep on heating it, take iron for example, at room temperature it is dark and black, you keep on heating, it will become red, and then it will start giving you radiations, it will become red, yellow. As the temperature increases, as the temperature of the metal increases, it will give you all kinds of radiations. So, the essential the blackbody radiation has been extended to explain the emission and absorption processes. It is very simple. At room temperature, it absorbs all. At higher temperature, it starts emitting the radiation, because it gets hot, you will see red color, yellow color of the same metal. So, our eye is sensitive to lights. So, the ions, atoms and molecules in general exist only in certain discrete energy states. This is the basic quantum mechanical theory. So, when it changes its state, it absorbs or emits the radiation amount of energy exactly equal to the energy difference between the two levels, between these states. So, if I take certain amount of material, so I give energy, material gets heated up. So, the electrons and other things will get excited, they will start vibrating, and after some time the electrons will go to next higher energy level, you supply more energy, electrons will go to still higher energy level, some more. So, at some stage they will escape from the electromagnetic field of the atoms and the molecules. So, this is what happens normally. So, and whenever there is a change in the excitation, in the energy state, the change is exactly equal to the energy difference between the states. It is not continuous, so it is quantumized. So, it is quantized. Therefore, during transition from one energy state to another, the frequency or wavelength of the radiation emitted or absorbed is related to the energy difference between the states. The equation is very simple, we have been discussing it all the time. E1 minus E2 is equal to h mu hc by lambda, where E1 is the energy of the higher state, E2 is the energy of the lower state. This E1 and E2 are arbitrary, it can be E2 or E1 also, it does not make any difference. What we are simply saying is, it is one is higher state, one is lower state. The energy difference is given by hc by lambda. So, in photoelectric effect we continue our discussion. What happens? For atoms or ions in the elemental state, that is hydrogen in the gaseous state, iron in the metallic state, and chlorine in the gaseous state, something like that. The energy of its states arises from the movement of the electrons around the nucleus. So, such energy levels are called as electronic energy levels. So, the electronic energy levels are always associated with the electrons moving around the nucleus. So, what happens to molecules then? In molecules, in addition to the electronic states, there is a possibility that the electrons are affected by other atoms in the same molecule, because a molecule is a group of atoms. So, an electron belonging to particular atom may be associated in some way with the other elements of the same group. For example, if I take COOH, the electron and hydrogen may be affected by COO atoms and their electrons, nucleus, etc. So, an electron in a molecule, the electron is always associated with the other atoms also, atomic cloud. Basically, we are talking about atomic cloud, and the behavior of the atomic cloud in atoms and molecules are slightly different. So, this we should understand. So, that is what we are saying. So, there could be some amount of vibrational and rotational states arising from the rotation of the molecules or functional groups of the molecules themselves. So, if you imagine hydrogen atom, it is a spherical atom, simple. But if you imagine a COOH group, so there will be carbon, oxygen, oxygen and then hydrogen. So, molecule could be a linear molecule or a bent molecule like this. So, the electrons, apart from going to next higher energy level, they could also be vibrating in the vertical and horizontal directions. Okay. So, the electron can occupy an electronic energy level, the next higher electronic energy level, but each electronic energy level is associated with a number of vibrational energy levels. And to extend the logic further, each vibrational vibrational energy level is associated with a number of rotational energy levels. So, the point is, you can imagine a tall building with a number of floors, stories, first floor, second floor, like that. There are number of steps. If you are standing on the ground floor and kick a football, you may hit the first floor or second floor, third floor, like that, depending upon your energy. And imagine that first floor, second floor are all representing electronic energy level. So, to reach the first floor there will be steps, but when the electron is a football is hit on the first floor, there is no guarantee that it will land on the first floor itself. It may land 1 or 2 steps above the staircase or 1 or 2 steps below the staircase, like that. I can imagine that the steps associated with the first floor, they are all vibrational energy levels of the excited atoms. Same thing happens with if I take it to slightly lower dimensions, each vibrational energy level again I can imagine as number of floors, and from one vibrational energy level, if the electron goes to the next vibrational energy level, it could be associated with number of smaller rotational energy levels. So, that is what all these steps are associated with the functional groups of the molecules around the center of the mass. Because if it is only hydrogen, I know that it can be a simple spherical molecule, but any other thing could be linear, non-linear and 3-dimensional, 2-dimensional, several possibilities of the electronic structure exist. So, the lowest energy state of an atom or a molecule exists at room temperature. This is a fundamental simple assumption. Why? Because at room temperature normally the energy is minimum. We are not supplying any energy. So, whatever is the room temperature, that amount of energy is available to all molecules. So, that is called as ground state. So, 99% of the atoms and molecules and groups, functional groups, etc., at room temperature, we assume that they are in the ground state. So, higher energy state, if I heat them, I am supplying energy. So, the electrons and molecules, etc., they have to go to next higher energy level. So, these are termed as excited state. So, we have two kinds of energy levels. One is ground state another is excited state. So, the excited state, when they reach when the electrons reach, the detectors are used in spectrophotometers, infrared, fluorescence, HPLC, etc. They all work on the photoelectric effect, and the equipment used to determine the current. Photoelectric current means effect means current is generated. So, you have to measure the current, and to measure the current what we need is a small electrical equipment, measuring instrument, that is known as barrier layer cell, photovoltaic cell, vacuum photo tube, photomultiplier tubes, diode array detectors, etc. All these things are required. The determination of the electromagnetic radiation and their energy. So, we always said the electromagnetic radiation will always can always be measured using the photoelectric effect. So, that gives us a tool to determine the effect of electromagnetic radiation on matter in which it interacts. So, what we are essentially saying is, take matter, allow electromagnetic radiation to interact, measure the electromagnetic radiation. Take out the matter, see what is the original condition. What is the difference? The difference is the amount of current that is generated whenever we are making measurements, and that is done by this photomultiplier tube, diode array tubes, vacuum tubes, photo tubes, barrier layer photovoltaic cells, etc. Okay. So, continuing our discussion, nature of interaction of radiation and matter, what we call the heat or supply of energy to a molecule, it is called as chemical stimuli. It may be in the form of heat, it may be in the form of electrical energy, or it may be just bombardment, or it may be a simple chemical reaction also. So, the stimulus, what happens? What happens to when the stimulus is given? The analyte species move from one energy level to another energy state. If you increase the temperature, they go to the higher energy state. If you decrease the temperature, they go to the lower energy state. In the process, energy is either absorbed or emitted or scattered also. So, information about the analyte can be obtained by measuring the electromagnetic radiation. So, this is what we are planning to do in spectrophotometry, and at this point I want to show you what is emission process and what is absorption process. Imagine here I have the radiation, thermal, electrical or chemical energy. I have the sample here, the process is emission. So, when the electron goes from ground state, on the look on the right side, the electron transition I am showing with a dotted line. So, when it comes back to the ground state, it emits the radiation that it has absorbed. So, whenever I am supplying a stimuli, it goes to next higher energy state, but when it comes back to the ground state, the amount of energy absorbed is lost, that is released. That is what we said, it can absorb, emit or scatter. So, in emission it gives you certain amount of electromagnetic radiation equivalent to the energy difference between the two states. So, this is emission. So, what happens in the absorption? Here the sample is here, incident radiation is at the back, transmitted radiation is on the right. So, the energy difference is again given out as heat, it is not the radiation. So, the heat is the effect of absorption. So, the amount of energy corresponding to the electromagnetic radiation before is higher, post sample interaction will be lower. So, this energy difference is known as absorption. The whatever amount of energy we supply is absorbed. So, when it absorbs, the molecules may go to next higher energy level. So, there are different types of emission radiations. When excited atoms, ions or molecules return to the ground state, excess energy is released as heat. This I already told you just now, and that is in the form of photons. The excitation we can bring it by bombardment of the elementary particles, that gives rise to X-ray, electric current, AC spark, etc. Beam of electromagnetic radiation also we can use for excitation. This produces fluorescence. All these things we will be studying in our course, and exothermic chemical reaction also produces some amount of light, that is known as chemiluminescence. So, we are going to study absorption, emission and chemiluminescence and fluorescence. All these are part of the spectroscopic molecular spectroscopy. So, we will stop here for 2 minutes, 5 minutes, and then we will come back. We will have another smaller session with respect to other properties of the spectra. Thank you.